This video is about linear approximations and differentials. Hello, this is Chapter 4, Applications of the Derivative, 4.6, Linear Approximation and Differentials. So you have already found the equation of a tangent line, and typically we use y minus y1 equals the slope times x minus x1. Well, a linear approximation, this is a function in its own right. So if I let some ordered pair a f of a, this is my x1, y1, and my slope is going to be the derivative at a, then we can rewrite this as y minus f of a equals f prime of a times x minus a. And then adding that f of a over, we get f of a plus f prime of a x minus a. And rather than using a y, we're going to use L of x. So this tangent line represents a new function, which we call the linear approximation to f at a. And provided that our function and our derivative of our function are easy to calculate at a particular point, then we can approximate points near a using this linear approximation. So f of x is approximately the linear approximation provided we're close enough to a. So let me explain that real quick. So when we have this curve here, f of x, and we have the tangent line here, L of x, if you zoom in close to a, so here's a right here, if we zoom in close, you can't really tell the difference between the two lines until you're a ways away. Once you get further away, the difference between those two lines becomes more apparent. But as long as you're close to a, we can use the linear approximation to approximate a function value. So if we take a look at an example here, we want to find the linear approximation to the function f of x equals the square root of x and use it to approximate the square root of 4.1. So our function f of x is root x, and the derivative of our function is 1/2 x to the negative 1/2. So let's find the function value at a. What's our a in this case? Our a is 4. So the function value at 4 is the square root of 4, which is 2. And the derivative at 4 is 1/2, 4 to the negative 1/2. Well, 4 to the negative 1/2 is 1 over the square root of 4. So we're going to get 1/2 times 1/2, or 1/4. All right, so let's find this linear approximation. L of x is going to be f prime at a, so 2, plus the derivative at 4, which is 1/4, and then x minus 4. If we simplify that, distribute our negative, we're going to get L of x is 1 plus 1/4 x. So distribute and collect like terms. So this is our linear approximation, and we would like to find, excuse my dog. Sorry about that. That was my little Jack Russell Terrier. We call him the Jack Russell Terrorist. All right, so where were we? We were at finding the linear approximation of the square root of 4 plus 4.1. So the square root of 4.1 will be approximated by this curve, 1/4 times 4.1, and we're going to get 2.025 approximately. All right, so let's take a look at what really was, if we use our calculator, what was that? Well, if we use our calculator, we get the square root of 4.1. Hold on. The square root of 4.1 is approximately 2.024845,673. So this is using our calculator. So you can see we were pretty close. But how close were we? Well, let's take the difference between the function. Let's take the approximate value minus the exact value. Well, we know that that's not exact, but we're going to use that anyway, the one from the calculator, divided by the absolute value of the exact value. And then we're going to multiply that by 100. So here we go. We've got 2.025 minus 2.024845,673 divided by 2.024845673 times 100. So we get 0.0000. Oh, excuse me. We only have 2 zeros. 0.00762%. So our error is very small in this case. Next example. Let's find the linear approximation to sine x at x equals 0 and use it to approximate sine of 2.5 degrees. So again, we're going to start with our function, which is sine x, and the function value at 0 is 0. The derivative of sine is cosine of x, and the derivative at 0 is cosine of 0, which is 1. So our linear approximation is going to be our function value at 0 plus our slope, f prime at 0, times x minus 0. So we end up with the linear approximation being just x. So let's find the linear approximation. Now we can't do the linear approximation of 2.5 degrees. That doesn't make real sense to us because we wouldn't plug a 2.5 in there. So let's take our 2.5 degrees and change it to radians, pi over 180. And we get approximately 0.04363 radians. So we're going to find the linear approximation at 0.04363, which is 0.04363. Cool. 363. The calculator actually in this case will give you 0.04362. So we're not too far off. And we of course could calculate our error if we wanted to. All right. Linear approximation says that a function can be approximated by L of x. So in other words, the function value can be approximated by L of x, where a is fixed and x is a nearby point. Well, if we look at this, the difference, f of x minus f of a, is what we call a change in y. So a change in y, we denote delta y, and a change in x, we denote delta x. So we have now delta y is approximately f prime at a delta x, where a has to be is in a differentiable interval. Probably didn't say that very well, but we'll talk about it. All right, so let's go ahead and just read this. Suppose that f is differentiable. In other words, we can take the derivative everywhere on the interval I, and that interval contains a. Then the change in value between 2 points, a and a plus delta x, the change in the value of the function between these 2 points can be approximated by delta y is approximately f prime at a delta x. All right. If you want to, there's a really great interactive figure in your My Math Lab. If you go to Course Tools and pull up the Multimedia tab and look for the interactive figure in section 4.74, there's an excellent interactive figure there. The interactive figure looks something like this, but you're able to slide your x in this direction and see how things change. So I want to make sure that you understand that delta x is the change in the x values. Delta y is the change in the two function values. Keep in mind that's the function, f of x. Okay, let's look at another example. Approximate the change in y if the function is x to the 8th minus 3x plus 4 when x changes from 1 to 1.05. So our delta x, 1.05 minus 1, is going to be 0.05. The change in y, we're going to call delta y, and we know that delta y can be approximated by f prime at 1 times the change in the x, which is 0.05. So in this particular case, if I evaluate my derivative, f prime of x will be 8x to the 7th minus 3, and we find f prime at 1, we'll get 5. So we're going to get 5 times 0.05 for a total of 0.25. All right, so uses of linear approximation. So if we want to approximate a function near a, we're going to use the linear approximation. And if we want to approximate the change in y, which is the dependent variable, when the independent variable changes, we're going to use this expression right here. So now I want to talk about the difference between dy and delta y. So we've been using dy. A differential is a change in the linear approximation as x changes. So we're talking about L of x plus delta x minus L of x. So the change not in the original function, but the change in the linear approximation. We denote that dy. So dy is our differential, and delta y, of course, is the change in the y values. In other words, the change in the function values, f of x plus delta x minus f of x. So the difference here is that dy, the differential, is the difference between the linear approximations, and delta y is the difference between the two function values. So if we have a function which is differentiable on an interval I that contains the point A, if the x-coordinate changes from a to a plus delta x, the change in the function is exactly the delta y. Okay? But if we use this L of x, the change in L as the x-coordinate changes from a to a plus delta x, in other words, the delta L, is going to be the linear approximation at a plus delta x minus the linear approximation at a. So all I've done here is plug those function values in. So the linear approximation at a minus, or a plus delta x minus the linear approximation at a, and we end up with delta L is f prime of a delta x, and of course delta L is our differential. So the differential dy is the change in the linear approximation. So we're going to call this dy. So d, and you can see that dy, and this is where that interactive figure is just really important. Dy and delta y are really close together as long as our delta x is getting close to 0. Quick note here, dx and delta x are always exactly the same. Those are the same thing. They mean exactly the same thing. All right, finishing this up, we use the notation of differentials to write a, okay, let's use the notation of differentials to write the approximate change in f of x, the approximate change in y values for the function f of x equals 3 cosine squared x. So I'm going to start here with our function f of x, 3 cosine squared x. And I'm going to find the derivative, which is, excuse me, using the chain rule, 6 cosine of x times sine of x. Oh, excuse me, derivative of cosine is negative sine of x. So simplifying that, we get minus 6 cos x sine x. Well, you might recognize, let's rewrite this. If I write it like this, you may or may not notice that 2 sine x cosine x is actually sine of 2x. So losing a little trig substitution there. So that's a nice simplified form of our derivative. We want to find the approximate change in the y, that's dy, and we know dy is approximately f prime at a delta x. So in this case, dy is approximately minus 3 sine 2x delta x. What does that mean for us? Well, that means that a small change in dx produces a small change in the function values of minus 3 sine 2x. By the way, let's just go back here real quick. Since dy dx and delta x are the same, we're going to write this as dx. So perhaps I should have done that up here, called this dx rather than delta x. All right, next video.